So today we are going to start Chapter 8, which is titled The Periodic Table. You would think this might come earlier in the year, but this chapter, there's many different parts to it. Includes stuff like what are more like the history of the periodic table, how was it discovered, plus the different patterns or trends, also known as trends on the periodic table. In fact, that's probably one of the biggest things in this chapter. It's known as periodic table trends or periodic trends. You don't memorize periodic trends. Periodic trends are sorry, you don't. Yeah, you will have to memorize these kind of periodic trends normally in a year. There is no math in this, so it's not like there will be no equations in this chapter. You would not. Even if it was in school, you would not need a calculator at any time for this chapter. So that's my only preface of this chapter. It's more of, just lots of different facts about the periodic table. Okay, so I'm just going to get started today. So a periodic table, as you know, we have our periodic table in most chemistry, most science classrooms. You probably see a large periodic table on the wall. My classroom there normally is a large, giant periodic table on the wall for reference, primarily. That was created in, what year was it? Around the 1860s, okay, plus or minus, 5 years. So the periodic table created by this guy named Dmitry Mendeleev in the 1860s-ish, and he took all the elements that were known at the time, this 1890s, and from that, noticed that there were patterns. And we're going to come back to that idea a little bit later. But let's go back to even further in history. This table here is not a periodic, it's just a table of elements. These were the elements that were known in, this is around the 17, I don't know exactly what year this is. This picture comes from the textbook, but sometime in the 1700s. What specific year, 1700s, I don't know. But at that time, they knew elements like hydrogen. I'm not sure what azote is now, because these are old names. Carbon, oxygen, phosphorus, magnesium these days. Lime, that might be, I'm not really sure what that one part specifically is now. But these sort of elements that were known at the time, and these were the relative weights that were known. That carbon, I think that's 5.4. Carbon weighs 5.4 times that of an average hydrogen atom. Oxygen weighs 7 times that of a hydrogen atom. We know it's actually 8 times, but whatever. This is, again, the 1700s. So not bad. And actually, now that I look at this copper, yeah, it's 55.8, I believe, 56 versus 1. If hydrogen is 1, copper would be like 55.6. So it's not far off. How do I know that? Molar mass on a periodic table. Okay. Again, there are numbers how they calculated this back in the 1700s. I'm not so sure. But those are elements that were known at the time. And when were all different elements discovered? You don't need to know the actual dates. So I want to go to the next slide. There we go. Let me move my head. Okay, so here are when different elements were discovered. Again, these are not, you normally would not need to know dates of when different elements were discovered. But some we've always known about since ancient times, like iron, copper, gold. No one person discovered it. No one civilization discovered it. The ancient Aztecs, whether it's the Egyptians or all around the world, people knew about gold and iron and copper. So no one person, no one group of people discovered that. That's always just been known. The Middle Ages till about 1700, stuff like phosphorus, arsenic, antimony, zinc, platinum. Most elements, or a lot of them, discovered from 1730s to 1840s, like hydrogen and vanadium. If you can't see these colors on your screen, these pictures are also in the textbook. So if you have a physical copy of the textbook, these pictures are awesome. This picture is awesome there, so you can see these colors better. Or if you download the notes, these are, it might be clear depending on what kind of screen you're looking at. And the most recent elements, 1965 and on, from Rutherfordium to 118, we have discovered elements 113, 115, 117. This periodic table, again, this comes from a textbook, this picture here. The textbook was written about 10, 15, roughly 15 years ago. So at the time, these elements were not discovered yet. And in that time, 113, 115, 117 have been discovered. And so we currently are at 118 elements on our periodic table. Some more recent ones. Also some recent ones down here: Neptunium, plutonium, americium, all these elements down here. So all these elements past uranium. Uranium is the last element on the periodic table that is naturally occurring. Okay, so there are, I forget, it's only 89 or 88 naturally occurring elements. The last natural one on a periodic table, element number 92 on a periodic table, meaning elements 93 and up are man-made. There's no such thing as plutonium mines. You cannot mine for it, okay? It's human-made. It does not exist in nature, on Earth at least, okay? If you're like, well, what about some exploding star in another galaxy? Let me this is on Earth, okay? So on Earth, there is no natural plutonium. There is no natural californium. Despite we're in California, there is no natural californium found in California. It's man-made. It's made in a lab. And in a later chapter, we can talk about how they are made. But a very general thing is they try to collide nuclei of atoms together and hope they stick. But that's not a very, very simple thing, because in general, they don't want to. Okay, it's not stable that way. So since it's not stable for them to collide and stick, it is actually quite difficult to make these new elements. If it was easy, we'd be way past 118 right now. And the techniques to do it is actually quite challenging, which is why there's only up to element 118. And most of these are so unstable. These elements are so unstable. They only last, some of them, only a fraction of a second. And so although you make it, they only last, maybe a few seconds or a fraction of a second. And then they break apart into smaller elements, more stable elements. So that's another reason why they're so difficult to make. In terms of naming of it, there's actual rules. If you so happen to discover the next element, you get naming rights, which is why elements like plutonium-94, why didn't name it that when they discovered it? Well, if you have uranium-neptunium, Uranus-Neptune, what's the next planet? Well, at the time it was a planet, Pluto, so plutonium, it just made sense. And this guy named Glenn Seaborg discovered element number 95, I think 95, 96, 97, 98, 99 to 100, I believe. I could be corrected. But I believe he discovered elements 95 to 100, and we actually named the element after him, number 106, Seaborgium. He's an American scientist, and since he got naming rights, there are rules and names. You can't, just totally make up your name. But since he got naming rights for it, and there's already polonium after a country, Poland, and francium after France, and germanium, GE, after Germany, why not one after America? So that's why element number 95, americium. Curium, after Marie and Pierre Curie. 97, 98, Glenn Seaborg was a professor at the University of California, Berkeley. So that's why, in terms of naming them, they were named after the country. Why not more the city and state? Berkeley, California. So that's where some of these names have come from in the past. So in case you're wondering, like, where's these names? Why California? Well, you could kind of almost guess that. Whoever discovers it gets naming rights. You can't totally name it after just almost anything. There's rules like, there's technical rules like you can't name it after someone who's still alive. I don't make these rules, but I'm just telling you the technical things about it. Okay, going on. So that's a bit of discovery of the elements. Again, these are not names or dates that you would ever have to memorize. Okay, so our ground state electron configuration. I don't know why there's a green line there. It's not supposed to be there. But so here's the electron configuration, so the outer electron configuration of the elements on the periodic table. Notice what we see about all the alkali metals. Group 1. They end in 1s1, 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. They all end in something s1. Group 2 elements, alkali earth metals. They end in 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. They all end in something, some number, okay, principal quantum number, and s2. Going over here, group 3a elements. Going over here, notice they end in something 2s2, 2p1, 3s2, 3p1, 4p1, 5p1, that's a 6p1. They all end in something s2, something p1. Followed by carbon ends in p2, S-silicon p2, germanium 2p2, or 4p2, tin 5p2, 6p2. They all end in something p2. You can guess, and you can also see on the screen, what does this group 15 or group 5a all end in? They all end in something p3. What about the oxygen group? What do they all end in? You can see on the screen, they all end in something p4, followed by obviously p5 and p6. The noble gases end in something p6. There is one exception. Let me go back. Notice that helium here, just 1s2, there is no such thing as a 1p level. So it just ends in 1s2. There is no 1p level, so just a 1s2 for helium. Down here, scandium. Scandiums would be something d1. This would end in d2, 3, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9. Over here, and in d10. Remove my face. Down here, we have the 4f, 1, 2, 3, 4, 5, 6, 7, 8, all the way down, and 5f's. So this is the same as our last chapter about, if I don't have the last chapter notes pulled up, but if you look at the table of the last chapter, this is also known as the S block. Over here are known as P block, in the middle of the D's, and down here the F's, specifically 4F and 5F. Okay, other things we need to know about the periodic table are parts of a periodic table. So let's start with some easy ones. These here in blue, it actually includes zinc, cadmium, mercury. I didn't make this. This comes from a textbook. So the elements in blue, including zinc, cadmium, mercury, they are known as our transition metals. So these elements down here are known transition metals. You probably already knew that. Our noble gases is the last column on our periodic table. Not on here that you should also know. Alkali metals, group 1. Alkali earth metals, group 2. And the halogens, group 17 or 7a. So those are the halogens. Yeah, halogens. I was just thinking noble gas again. Last column's noble gas. Okay, other things on here. Group 1, group 2, 1a, 2a, also 3, 4, 5, 6, 7a, but not including noble gases, are also known as representative elements. Representative elements are elements with S and P block elements that, not including noble gases, that are not full. Non-full S and P block elements are known as our representative elements. They are the ones in gray in this table. Down here, of course, you see the lanthanide and the actinide series elements. Lanthanide and actinide series elements are down here. Okay, so these are just parts of the periodic table. You should know the different elements, different things on our periodic table. We'll continue on from here.